Hello, everybody. It is 5:18 p.m. Central Time on the 4th of July, 2019. It's Thursday here in the United States, and we celebrate the 4th of July. Hope you're having a good one. We are here on the Earthquake 3D live stream. And you, if you are new here, may not know what you're looking at. You're looking at a three-dimensional representation of the globe, and we're using the USGS and EMSC earthquakes to provide us a good view of what's going on around the planet. You can see me here on the screen, but I will be disappearing in about 2 seconds here as we open up a display capture to go in and get into the nitty-gritty. I told everybody to come over here because I was going to be doing an update explaining how to forecast an earthquake. So if you don't know about my past or anything about what I do here on the stream, we watch earthquake activity and then we watch for new activity to develop out in areas around the planet. Now, over the past 7.5 to 8 years, going on 9 years now, at December will be the start of year 10. But for the last 7 to 8 years, I've specifically focused on earthquakes, monitoring where they were striking at first, and then we started to notice, myself and a few other people, but me mainly the figurehead on this, started to notice deep earthquakes starting to occur. And of course, they've been happening for a long time. But what we started to notice from this was from the deep earthquakes, we then would see within a few days' time to a week, 7 to 10 days usually, we see a responding effect up above the deep earthquakes next to them. This is where everything started with quote-unquote earthquake forecasting. And we need to get into the correct terminology on this. I want to address this right before we get even into how to. First, we have to address earthquake forecasting in general, which is just like weather forecasting. We don't call it weather prediction. I mean, maybe in the back day we would call it weather prediction, but the proper terminology for this is forecasting. Forecast can change as situations develop or as Mother Nature responds in a different way than expected. Also, just like weather forecasting, we can get an area or a region correct and have the smaller details, like for instance, like a hurricane landfall. You can forecast out, several days where you think it's going to make a landfall in a broad area, and then down to the final day, they can get it down to a very fine point as to where the hurricane is going to make landfall. So much like hurricane forecasting, earthquake forecasting, we do rely on larger areas, a few hundred miles across. I try to look within 200 miles of an area to try and get it down to. Many times it's 300 or 400 miles. Sometimes it's right down to the point. So, I'm one man, by the way, no big operation behind me, and this all comes from observation, so there is no theory of mine. We'll get into why I think these things are happening towards the end of this, but first let me explain the physical processes. So first, there are deep earthquakes that I see happening, and other viewers and other researchers see happening. Within days, we then see shallower, larger earthquakes pop up around where the deep earthquakes are. Now, Earthquake 3D here shows us our earthquakes raised high off the globe. These represent the deep earthquakes. So the higher they are off the planet, the deeper they are into the Earth. This is taking us down into an area down below the plates called the asthenosphere, which is a just complex term to describe the semi-melted magma down below the plates. So down below the plates, we have semi-melted magma, and in that area, we're seeing earthquakes develop out right below the plates, even further down below, a few hundred miles below the plates, in the magma, semi-melted. Well, from that, then we see something happen, and I'm going to turn on a video here now, which you should see in the upper right-hand corner, and I'll make this a little bigger. You see on the screen here now how this is generating a circular-shaped wave. Okay, that circular-shaped wave that we have on the screen is a concentric wave that's in a pool. But I want you to imagine this happening down below the plates in the magma, and it comes in on itself and focuses in on a singular point, hammering up into the underside of the plate. Now, this singularity that happens here, I believe, then spreads out across the plate boundaries. So the plate boundaries, then, you'll see lit up with earthquakes all the same size. Now, this next video that's playing here, again, it's blocking the globe, but I want you to see it really good. This is a standing wave experiment. And this standing wave experiment shows waves in a tank that are all at 0.6 hertz. Now, that sounds complex. Let's just say a broad wave in a tank. And these broad waves, or very low frequency waves, build on each other. Instead of interfering with each other, interferometry, it actually builds on itself, and it forms what's called a standing wave, where the amplitude or the wave height or the power of the wave builds on itself. And what you're seeing here are the waves start to take a uniform shape, all the same size, and they are moving through the tank in this case, and the tank, of course, containing the waves then fill in each other's middle points as it moves back and forth. Watch as one peak fills the next valley. And they're all the same size. So what I think is happening here is as that hammering action comes in that you saw in the first video, it then spreads out through the plate boundaries. And each wave that stands up, you see again, fills in each other's middle point. Each wave that stands up, I believe, is causing the earthquake. I think at the highest point. Now, it could be at the lowest point or anywhere along the wave. Nonetheless, we're getting uniform earthquakes all about the same size, just like standing waves in a tank. But instead of in a tank, it's then spread out across a vast distance. Now, I'm going to turn this video off. We'll get into the second part on this in just a little bit. So, the deep earthquakes hammering up on the underside of the plate, concentric wave coming up from the underside in the magma, causing the deep activity to hammer in like a jackhammer on the underside of the plate. Then spreading out across the plate, through the plate boundaries. Now let me show you a USGS plate boundary map. This is going to make a lot more sense. So now we're on the USGS website, and we're going to go up in the upper right-hand corner and turn on tectonic plates. You see these red lines? These are spots where there are fractures between the plates that start at the surface and go all the way down through the plate, down to the asthenosphere, where we have our deep earthquakes hammering up, for instance, here. So we have a jackhammering action coming up on the underside of the plate here, and then downstream, and I call this downstream, I'll explain that in a second, but then over to the west, we could also say, then we see the same sized earthquake spread out across the whole plate boundary in the course of a few days' time. So in this case, look, we've got a spread of fives, all the same size, 5, 5.1, 5, 5.1, 4.9, 5.1, and then sandwiched in between here, we have a 6. A larger earthquake sandwiched in between our other sets of 5s. We have a 5.6 on one side and a cluster of deep earthquakes on the other, and then sandwiched in between, like a sandwich being pushed together. Let's get back over to the USGS plate boundary map right here. So next to New Caledonia, this area has pressure coming up on the underside, this area already moving, and the middle point comes under pressure and releases with a new earthquake, which is then represented in this video that I was just showing. Oh boy, okay, well we have to wait for it to play all the way through. Oh boy, I wasn't prepared for that. Okay, I wasn't prepared for it to start over. And, well, I'll explain as we're going along here. So our deep earthquakes hammer up with the concentric wave, then it spreads out through that wave tank where the equidistant waves space, the standing waves space out and drop off the same sized earthquakes, I think at the peaks. Then the middle points fill in with a fulcrum point. Now, everybody understands a 2-arm scale. We've all used them before. Scales of justice. Okay, you would put weight on one side of the scale and weight on the other, and the combined weight combines in the middle at the fulcrum point. Another example is on a children's playground. This is just simple terms here. Children's playground, you have a seesaw or a teeter-totter. And the seesaw teeter-totter, you have 2 equal-weighted children on either side, and they're pushing their legs up and down, and they're bouncing back and forth, balancing on that middle point. That middle point is the fulcrum point. This takes us over to the video again, which now I'm going to explain. The fulcrum points are filled in as the wave spreads through the tank. Now let's make this full screen. As the wave spreads through the tank, I believe this is like the plate boundary. So this tank represents a fracture in the plate that starts at the surface and goes all the way down through the plate. And the wave spreading through it drops off equal-sized earthquakes all the way along the way as it moves through the plate boundary. But it's coming up from down below, from that hammering up wave that you saw at the start. Okay? So as that's happening, let's get a closer look on this. And what you'll see, not only are the fulcrum points filled in, but as the waves take the same size, they reach an endpoint and they bounce back. That's what forms the standing wave. So it's a wave forced back in on itself, and instead of interfering with each other, they combine and basically the power increases, amplitude. So the next video here is from UCLA. This explains the fulcrum points, I think. I just found this video recently. And what we're seeing here is a shake plate. And on the shake plate, we have a vibrating liquid. Now this applies to waves and liquids, but I also think this applies to VLF, SLF, very low frequency, and super low frequency, just like we would see in an earthquake, traveling through a rock or a portion of the plate even. Now look at this. The standing, once an outside force introduces a shaking onto the fluid, the already shaking portion, the little shake plate, carries on the standing wave in an actual standing wave that stays in place. Now this gets into what's called a soliton. This gets very complex. Soliton and solitary waves. So a soliton and a solitary wave forming in a fluid, but I also think this is happening inside the plate boundary. This little container that the fluid is in represents the plate boundary, and the wave that you see happening here in the fluid is representing the VLF or SLF, very low frequency, inside the plate. Look at that, hammering in place, all the same size. Okay, now they get a look at that. It's a strobe shot of it. Now, this next part with the balancing bolts, this is again a UCLA experiment on a shake plate. This is for acoustics. Acoustics just like sound waves. But as we know, acoustics and earthquakes are very similar. I mean, the same kind of physics can apply. So these balancing bolts right now are not moving at all. Once the shake plate is turned on, you're going to see equal distribution of force across the mass, which is represented by the free-floating shake weights. You see where the shaking starts? Shake weights. Haha, that's funny. The weights shaking. Now you'll see an equal distribution across the mass, since we have the same amount of weight on each string and it's spread across the shake plate, or well, in this case, acoustic. But you see it, equal distribution across, and we're getting the same size. I think this is, again, a representation of the same sized earthquakes going across a fault. Now look what happens in the middle, between the two areas that are moving on either side. They zoom in on it in a second. Notice, it's a quote-unquote silent zone, or a quieter zone, or an area where there's not much movement, a dead zone in the middle. Now, what does that have to do with anything? Well, let's just go ahead and minimize this as low as possible now. Get it real tiny up here in the upper right-hand corner. The fulcrum point, that fulcrum point that I just showed you with the screws swinging back and forth, that fulcrum point is the combined area total, but it's not a silent zone. It gets hit with an earthquake. So first there's a silent zone, just like in that experiment, but then it gives way and the combined total of both sides adds up in the middle, just like a two-arm scale. So we're talking about an accumulation of power or energy on either side of an area, and then it adds up in the middle. So what's the middle? How do we find the middle? And this gets into the basics of earthquake forecasting. Now that you understand the principles behind this, I think it's going to make a little bit more sense. So we look between our sets of earthquakes over the last 48 hours. Now, I've determined 48 hours. Somebody else who comes along in the future may do it at a longer period or a shorter period. But I've found that 48 hours is a good representation of what's moved in the last few days and what's getting ready to move in the next week. So I'm trying to get it down to a week's time for humans' sake. Maybe someday people will get it down to a daily point. At this point, we're down to about a week and down to about 200 miles, between 200 and 500 miles, which is regional, and that's good for large earthquake forecasting. We don't forecast anything under 4s except for in the United States. We'll get into the US in just a moment. So deep earthquakes come hammering up first. The deep earthquakes have a power conversion. Take a look at the screen. Here on the screen is a chart developed by two of our fellow researchers, Bella and Rebecca. They're two of my moderators, by the way, because I trust them in the information they post. And what they've found, what I've found, is that there's a translation of power from the deep earthquakes. There's actually a formula that can be used. Now, I'm not going to get into the mathematics behind the formula. You can contact Bella and Rebecca, who have this thing copyrighted, and you can check with them. But I show it on a regular basis. This is depth to magnitude conversion. And the green on the chart shows depth. And the magnitude is to the right, and that shows what we add on to our deep earthquakes. Let me explain. So, let's turn off the chart. Get back over to our deep earthquakes. Here's a deep 5.8 earthquake down at 574 kilometers down below the plate, 300 miles, something down in the magma down below. Now, this is going to hammer up on the underside of the plate. When it hammers up, it's going to come up out of the fluid and go up into the solid. It's going to come up out of the magma and go into the underside of the plate. So this deep 5.8 at 574 kilometers, we look on our chart. Go over to 500 column 570, and we can go, or 550 column, and go all the way down to the bottom of it, and it says 574 at the bottom, and right next to it, it says 1.15. And move my mouse around here behind it. 1.15 magnitude is what we add on to the 5.8. So we add on 1.1 magnitude to 5.8. That takes us up to 6.9 potential off this deep 5.8 earthquake, 1.1 magnitude larger. So a deep 5.8 happens. Then we watch for a shallow 6.9. Let's just say watch for near 7.0 next to this deep earthquake. And that's just if it's on its own. When we have multiple deep earthquakes, we have what I call a relay runner effect, where one passes on to the other, and it carries on the race around the plate. That's happening now, by the way. We'll get into that further on in the update here and the explanation. So deep earthquakes caused shallower, larger earthquakes. And then we look up between our sets of deep earthquakes and we find our middle fulcrum points. We look over 48 hours. That helps reduce the areas down. So in this case, this is a perfect example. We have 3 overlapping areas. Now the rings help. These range rings on Earthquake 3D really help. But we can even turn them off. Whether they're on or off, you should be able to find that middle fulcrum point between the sets of earthquakes. Let's use this area right here as the first example. Then we'll get into this and these other earthquakes going back over to the east. This is a perfect example, though. Look where the 2 sets of rings overlap. They overlap in eastern Papua New Guinea. So we have 5.0 activity on one side, 5.1. We have 5.0 activity on the other. But I just told you, this deep 5.8 is going to be causing something like a 6.9 over here in this area, and we look between our sets of quakes. Well, what just happened here where these 2 sets of earthquakes overlap? The biggest volcanic blast I've ever had to report on, Ulawan volcano just erupted right here, and right next to it, Manam, also the day after sent off a 55,000 foot high blast, but 63,000 foot high blast at Ulawan and a 55,000 foot high blast stratospheric both within a day of each other right here where the 2 sets of rings overlap. That just happened a couple days back. Now the earthquakes also just happened a couple days back. So this spot would be spot number 1 I would watch for the shallower, larger earthquake to come up at. First of all, because there's been big volcanic activity there. Second of all, because it's an overlapping area at the perimeter of the areas that are moving. Now let's go back. Let's go back over to the east. Again, we're looking at 48 hours worth of earthquakes here. So, I mean, again, we have to limit ourselves for the amount of movement to base our decisions on. So there's really only 1 or 2 other spots to watch. The other spot to watch is where the rings overlap here, the middle fulcrum point. One final point I'd like to make about the fulcrum points, we don't just draw a straight line between them. We go around the bends of the plate. In this case, we would go down. Let's follow the mountain range here. USGS plate boundary map also shows it. We would go down, around, and back up. Right? So it's not just a straight line between them. We go following the plate boundaries. And then that determines our fulcrum point between our sets of quakes. In this case, right here, and in this case, right here. Pretty basic stuff, right? Finding a fulcrum point between 2 areas that are moving. That's the dead zone now, by the way. Just like the UCLA experiment that I just showed you in that video, where the bolt was hanging in the middle, not moving, and we have areas moving on both sides. This is the area currently not moving. But guess what? It transfers. The solitary wave transfers. Let's get back over and show it to you one more time. So, here we are back at the UCLA experiment, and equal distribution of force going across the bolts on the shake plate. The middle point is the quote-unquote fulcrum point that remains silent, and then these areas move, which is going to be the next portion in this video. So as areas move, then there's a transfer. The fulcrum point starts to move. The middle point, it makes sense, right? One area is moving on one side, one area is moving on the other, then the middle point gets hit, and that divides the area. And then there's 2 areas that are moving, and that area gets divided. Think of it in musical note terms, dividing it from a 4/4 to what is it, a 2/8 or whatever? I mean, going in an eighth and then 16ths and then 32nds and so forth, dividing in half and half and half again. That happens. Now, in this, watch as they move the blade through the fluid. This is a transfer of a fulcrum point. Now, imagine this being the plate moving instead of a person with a knife. And look what happens when they take the knife out. The fulcrum point has transferred over to the right-hand side of the vibrating plate. So while there's small vibrations coming up through the liquid and you introduce an outside source, in this case the plate moving, that middle fulcrum point can transfer to whatever side it's preferring. The fulcrum point doesn't base upon a teeter-totter principle now then. even though it is a two-arm scale principle, it's out of balance. And the wave compensates on one side or the other. Look. Now we have the combined total of the wave compensating on the left-hand side, while the right-hand side remains completely silent. Now, this is in fluids. This should be mind-blowing for anybody who's into geophysics. Now, the next portion on this shows middle silent zones, again, an equal distribution of force from two angles. We got a side view and a view from above. The view from above, what it shows us is an equal distribution on both sides. Now, I believe this is because the wave is spreading out on both sides. Basically, what you're seeing is a visual representation of a wave physically. Think of that like a wave going up and down. But this is looking down upon it, so really it's going side to side. Now, check this out. On the right-hand side, we've got more movement. On the left-hand side, we've got lesser movement. That's a transfer across the mass. And in the middle, between where all the movement's happening and where the lesser movement's happening, between the right and the left, they zoom in on it. Look at that. So we have a breaking middle point as the zone transfers. As it transfers, that middle point then becomes a focus point. Now this next portion. This is a solitary wave. This is done. Now this is an example in a fluid again. Watch what happens as this transfers. I want you to think of this going through the fault and this not being a fluid, but it's coming up out of the magma. Traveling down, going down across the fault all at once. But it's coming up through the fault instead of going, again, this is a fluid in a tank. I want you to imagine this down in the magma down below going through the fault. Boom, hits a point where it's reflected back. Our standing wave starts to form. That takes us back to the start of the video where the standing wave forms down below the plate. Okay? So I hope I've explained that portion of it very well. Now let's explain the fulcrum points here, back behind it. What size magnitudes do we look for? Well, I told you, 5.8 here would be causing up to a 6.9, and we just had our big volcanic blasts here, and this is the spot where the rings overlap. Papua New Guinea is where we're going to watch eastern Papua New Guinea. That's one example. Back behind it, I would expect lesser activity, but still large. So less than the 6.9, let's put it at 6.5. Let's cut it in half, and half it again by the time we get back over to next to the deep earthquakes. So we'll take it from 6.9 down to 6.3 to 6.4. Then we'll take it from 6.3 to 6.4 down to 5.8 to 5.9. We're going to have it and have it again. We're going to take off a half magnitude each step back towards the source, because I think this is going to come up all the way over here. Now, speaking of coming up all the way over here, there's many professionals that are probably listening right now, and they'd be mind blown to find out that I've got studies linked down below that are now fully confirmed by teams of scientists, not just a few. Not that that matters to you. I mean, consensus shouldn't matter in science, but teams of scientists now proving that earthquakes are related over 1,000 kilometers away. Directly. Now, it's not that one earthquake causes the other. This is a fundamental principle I want you to get your head around right now. One earthquake does not technically cause the other earthquake. It's that both earthquakes, whichever earthquakes you're talking about, are caused by an inundating force that saturates the plate first and creates these standing waves that I was just showing you in the video. Those standing waves then reach a pinnacle point or a breaking point that then drop off the earthquakes along the way. As this force travels from region to region. First it comes up from down below with the hammering action, then it spreads out across the plate boundaries, dropping off these equal-sized earthquakes. Once it gets to a solid portion of a plate, it then is absorbed by the plate. It's amazing. The force gets absorbed from the plate boundary into a plate, like Asia, for instance, here, and transferred across what's called a craton edge. Now, a craton edge is just the edge of an interior solid portion of a plate. There's deformed edges and craton edges that are solid. So the solid craton is the center portion of the plate, and the outside edge is the deformed edge. Usually mountains form along those deformed edges, and we see earthquakes spread across those craton edges. I'll get into that in a moment as well. Let's recap. Deep earthquakes cause shallower, larger earthquakes. We look to our middle fulcrum points between whatever sets of quakes exist over 48 hours in the region around our deep earthquakes. When I say around, I look up to a few thousand kilometers in each direction, following the plate boundaries. So we have plate boundaries this direction. Now you're going to notice I've got two large arrows here pointing over to South America. The Pacific plate has fracture zones that go across the Pacific plate. You see them here, equal distantly spaced, almost, like latitude or ladder rungs. And you can go all the way down here, and the equal distance spacing stops right about here. So here, 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 here. These are all fractures through the plate as well. They're just like the plate boundaries, but they don't move. They're fractures through the plate that start at the surface and go all the way down through, but they don't move. They're through the plate. And I think we've proved this overall, that these act like superhighways as well to conduct the energy across over into South America. Now, something about these fracture zones, here, 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 they all go back to this undersea mount chain. You see this? This is Hawaii right here. But you'll notice Hawaii makes a V or a Y off this chain. The chain actually starts up at Kamchatka, Russia, comes down to the Hawaiian island chain. But then you'll see it carries on here. Now, this is an undersea supervolcano, by the way. So from the undersea supervolcano, we have a distinctive line of undersea mounts. These are all volcanoes. And it goes down and makes a crescent shape or a curve that goes back up into South America. You see that? Now, from this crescent-shaped curve and going all the way back up over to the east, we have the fracture zones that are equidistantly spaced. To the west of here, there are two spots. This and this that goes through America Samoa. Look where it connects back to. It connects back to our deep earthquakes. So we have a bunch of uplift happening on this side. You know how I know that? All the undersea mounts and volcanoes and islands that make up this region. But once we get to this undersea mount chain, it stops. And we don't see much beyond there. Over to the east, it's just nothing but fracture zones and very deep ocean. So there's an equal distribution of force or power being put out from this spread. Let's back this out and show it to you again. From Kamchatka all the way down, back over, and crescenting into South America down here. So equal distribution across this coming from this, which means this has been happening for a very long time. And as the force flows across over into South America, it hits South America like a wall. So first the force starts down below the plate here, just like the 5.8 example I used here, and just like the 6.9 example we used here, we would watch for a significant sized earthquake to come in over here, over in Ecuador, Colombia, that's just a hair less than what's striking all the way over here. So in other words, if we're going to look for a 6.9 to come up off that 5.8 here, I would look for something in the mid-range 6 level to be popping off here in the next few days. Equal distribution of force across the mass. Remember, it doesn't matter the size of the mass. In this case, the Pacific is huge, but it's going to distribute itself out this way and this way, following those fractures. Now, why? That jackhammering force that I showed you in the video, coming up out of the wave pool where the concentric wave hammers in on itself, it's going to distribute out equally across the underside of the plate. Guess what's the first thing it hits on the underside of the plate? Fracture zones. Fracture zones and plate boundaries then go up through those and reach maybe faults up inside the plate somewhere and volcanoes. Do I explain myself clearly so far? Okay, I think I do. Let's jump further over to the west and give you another example. So let's get back over to the USGS plate boundary map now. The red lines. Follow the red lines. Look where they go. They go over into Asia up through Myanmar, make a bend through Nepal, north of India, back down through Pakistan, over west through Iran, Turkey, into Europe, up into Italy, out to the mid-Atlantic ridge. So remember this shape, because now what I'm going to do is take you over and show you a matching set of earthquakes that mimics the inside line of that, going up just beyond Myanmar, into China, into the Himalayan range, over here right at the tip of our arrow at the Pakistan-Afghanistan border, then across Iran, then across Turkey, then up into Italy and dead ending into Italy here, but then picking up down here and going out to the mid-Atlantic ridge. That is the exact trajectory of the plate boundary. So from here, mid-Atlantic ridge, let me show you. 3.0 earthquake just struck. That's the most recent. Now let's trace it back. A 3 struck yesterday over here last night, and a 3.3 struck here yesterday last night. So first these two struck, then this. So it's moving from here to here, the energy. So we can trace it back further. We have a 3 here, we have a 3 here, we have a 3.3 here. We go back up into Italy, follow the plate boundary back down across Greece, go back here, then we split. Go down across Israel, where the Dead Sea just got hit 2 days ago, and we go down across Iran, both following the plate boundaries. Look one more time. Follow the earthquakes here. Let me turn on the rings so you can see this. I'll wait for this to refresh to get the most current events. There we are. So let's trace that back again, going along the plate boundary from here to here, back up to Italy, back down across Italy, going across Greece, across Turkey, back across Iran, back over to Pakistan, Afghanistan. That's a perfect match, isn't it? Here, back to here, down through here, back over to here, back over to here. Now we can trace it back further. We can trace it back around, back around, back around, and back down. That means the energy is being introduced over here, is transferring across here, and going over to here. That's what it means. And there's an equal distribution of the same sized earthquakes across that mass. Look, 4.2, 4.2, 4.6. There's another 4.6 that struck out here, by the way. You'll have to take my word for it. Another 4.1 and 4.0, add them together, it equals 4.2. Going to the west, we have another 4.6. So the same amount of energy that was deposited on the plate boundary ended up on the plate boundary. And that means this 4.6 here, well, guess what's going to happen out here? We're going to see something in the mid-range 4 transfer over out to the plate boundary. So we're going to look for our letter X to get hit up at Iceland with a new 4.5 to 4.6. I've told people 1,000 times, I'll tell you again, the same sized earthquakes that strike in South Europe tend to strike out at Iceland, Azores, and Svalbard, North Pole, within a few days' time as the force transfers across Europe, which is my next step on this to explain to you the arrows in Europe. So you can follow the arrows back. The arrows just show us, like a flowing river, which way we expect this to flow overall. Now, I just showed you the plate boundary map from the USGS. It matches most of our arrows, but you're also going to notice a few arrows that don't match anything on the USGS plate boundary map at all, do they? Right? USGS has no plate boundary across central Mongolia. USGS has nothing over in Eastern Europe. Why do I have a bunch of arrows there? Well, let's go over to Google Earth now. So, now we're on good old Google Earth. And we're going to turn off our borders and labels. Just pick your favorite country wherever you are. I mean, here's Italy over here, and here's Russia, and here's China. Let's turn off the borders, if I can find them. There we go. Now the plate boundary, remember I just showed it to you on the USGS map. One more time. Here, goes up through Myanmar, goes across Nepal, back down across Pakistan, over across South Iran. Let's trace that out. Oh, wait, you can see it from this high up on satellite? You sure can. So let's go up. You see where it makes this bend? We get a bunch of earthquakes striking right at the bend. Then going across, following it, it's a crescent shape. This is Nepal right here. Mount Everest. Series of earthquakes break out across this, and it goes up to here to a pinnacle, where then here's Iran, Pakistan, and Iran, Pakistan, Afghanistan. Now, doesn't it look like a flowing river from this high? Let's zoom in a little more. You're going to see those aren't flowing rivers. Those are bends in the plate. Those are bends in the craton. Iran technically is its own plate between Asia and Saudi Arabia, which Saudi Arabia is its own plate as well. Now let's get back over to the plate boundary map. You'll notice over in Iran, they only have the southern portion marked. See that? Southern portion, plate boundary marked. But look, like a flowing river where this would be a giant stone in a river and this would be the water flowing around it, look what happens. Goes up around this way and down around this way. Would you be surprised to find out that the earthquakes mimic this almost perfectly? And that the energy that's introduced here turns up over here, where they come together, like two flowing rivers coming back together, combining their force back together. So I've got two sets of arrows in Iran, and right at the tip of our arrows is where we see our most earthquake activity, usually in Iran. The combined force coming out of Asia. So let's take it a step back further. Again, USGS has no plate boundaries marked across, like I said, China, Mongolia, anywhere across here. Well, look what's here. See the mountain ranges marked in green? Let's go back over to Google Earth. You might be able to see it a little better. So here's the Taklamakan Desert in western China. But look to the north. See this? And see this? Now we follow across this back over to here where we get nudges coming out of North Japan. This gets me into the Northwest Pacific with our deep earthquakes again. See our letter D's on the map here in South Japan. Here, there's two of them in Indonesia. And here in Fiji, there's one. Now, those deep earthquakes strike at our letter D points. This is a forecast area point. I put the D's on the map there years ago. It's a regular occurring spot for deep earthquakes to happen. You can forecast it. You can wait for it to happen and then watch for the shallower, larger earthquakes to come up. In Japan, for instance, when we have deep earthquakes here. But we're going to go one step north. Here, our final letter D. This spot is a spot where we normally see deep earthquakes come up after major shifts across the whole Pacific that affect the South Sandwich Islands. Now, this gets me into a primary principle of something I discussed going back 7 years. 7 years ago, I proposed that earthquakes on the opposite side of the planet are related to one another. That's called the antipode. And we were seeing, and I observed many times myself, 6.0 and greater earthquakes, and now 5.0 and greater earthquakes, striking on both sides of the planet within a couple days of each other, within down to a hair of a point of one another. That's latitude, longitude wise, on opposite sides of the planet. And the opposite side of the planet from where this letter X is, we go over to our letter D. So we see earthquakes strike down here, and then within a few days, up here, we see a new deep earthquake come out and start the cycle over again, pushing on the underside of the plate again. Same with these spots here, off the coast of Japan, our antipode, all the way around down here at our other letter X. So when I start to see these, and I see them get hit, I started to relate these over distance, and then studies came out and confirmed everything I was talking about. The antipode studies are linked down below on YouTube, down below on Twitch. You can go read them, Scientific American, blah, 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 and they've talked about the antipode earthquakes, opposite sides of the planet getting hit with deep earthquakes and shallower, larger earthquakes, both having an effect on each other, my contention. So, let's recap one more time. Deep earthquakes come up on the underside of the plate, hammer out, spread out in what I believe is a standing wave. That standing wave drops off equal-sized earthquakes all the way along the way. So we've, in other words, found the force that causes earthquakes. VLF, SLF, traveling through the plate boundaries, coming up from a hammering action down below. Drops off equal-sized earthquakes along the way, then the middle points are filled in with shallower, larger earthquakes after these deep earthquakes happen. So two things happen. First, there's a spread of same-sized earthquakes, and then the middle points are filled in with shallower, larger earthquakes. Then it hits a plate, and the plate absorbs the energy and transfers it across the craton edges. Craton edges carry the energy, like the plate boundaries, and transfer the same-sized earthquakes all the way across, going out to a termination point. The termination point is really, we should call it a recycle point, because once it gets to the mid-Atlantic ridge, this energy or power or force can't jump over it. It's in the ground. It can't jump over many miles. And it can't go down underneath. It's a fracture that goes from the surface all the way down through. The mid-Atlantic ridge is a fracture zone as well that quite literally goes all the way down to the asthenosphere far down below. So when this energy hits the fracture, it goes back into the planet. Now this is where we get into some funny physics and some crazy core of the earth talk, which is that it's recycled through the planet and comes back out on the opposite side within a few days, starting this almost tidal cycle over again. So earthquakes, we can know when we see deep earthquakes, we can then watch for shallower, larger earthquakes to strike within days. Using the depth to magnitude conversion chart, it really helps. Excuse me while I get a sip of my drink here. It is 4th of July, you know. So, getting back into it, for the United States, for Central America, for South America, how do we do forecasting? Well, it's the same principles apply. The fulcrum points are sought out, and the only difference with the United States, we get our energy last. The energy starts over here, transfers over to the West Pacific, hits Asia, brought over to Europe. First stop. Second stop goes up across Japan, following our plate boundaries again. Deep earthquakes hammer in, the relay runner effect takes place. More energy is added in. Or think of it like this. Multiple people lifting on one side of the object here, and another set of people lifting on the opposite side of the object here. And if we get any more here, it's like multiple people lifting on the underside of something heavy. Eventually, it's going to start to move, and it does. Once it starts to move, the adjacent plates begin to compensate, and we get what I call compensation movement. I had to come up with all these terms myself. Compensation movement that happens across the plate boundary. Again, same-sized earthquakes dropped off along the way, and then we see it all pool up and strike at a point, a stick point, if you will, like a flowing river reaching a dam. Now, this past several days, we saw this happen. So first, starting over here in the West Pacific, a series of deep earthquakes happened. A deep 6.4 on the Izu Ridge you see raised right here off the globe. So this is like a really strong person lifting on the underside of the plate, and several very fit people, but not as strong, lifting as well. So they all lifted within a few days of each other. Then a spread went up and around the plate boundary. I mean, if earthquakes were random, they'd be all over the place. They're following the plate boundary, and it's the same size. One more time, take a look at the fives. Look how the fives spread equidistantly going from Taiwan, 5.2, 5.1, 5.0, and then boom, the cumulative total of all this, take the 5.2 plus the 5.1 equals 5.3. Add in the 5.0, might equal 5.4. What do we get up here in Alaska? A 5.3, and boom, big swarm broke out right at the tip of Alaska on the North American Craton. The Craton is defined by the mountains. You can see them. The North Arctic Circle. So this all accumulated up to here, and then last night, when this hit, I got on, and we issued a warning for 2 spots. First spot we warned yesterday was off the coast of Canada and northwest United States. 6.2 struck last night. Then today, the largest earthquake in decades has struck down in California. Now notice the spacing on these. They perfectly overlap. That's not me doing anything with the rings. I can turn them off. It's perfect spacing. So it's a whole plate being displaced at once in a day's time on a 6.0 basis. Now you could say the Alaska movement is a 5.3, but the swarm that struck with it, come on. So if you add all the activity together up in Alaska, it does equal about a 6. And then we have, so basically we have about a 6 up here, or a 5 in a swarm. Then we have a 6.2, then we have a 6.5. It's increasing. The energy added up, tallied up, the combined total, and struck. Now where did it strike? Let's go back to the USGS plate boundary map one more time. This is going to all make sense in about 2 seconds for you in California. So if you want to forecast earthquakes and you live on the west coast of the United States, first thing you have to watch is the West Pacific and all the deep earthquakes and the spread going over to Europe and going up across Japan and around Alaska and pulling up here. But then we get onto the west coast. Look where our 6.2 earthquake struck. It struck right at the Hecate Strait. Let's get back over and show you. Here's where our 6.2 is. Here's the Hecate Strait. Well, gee, isn't that right there? It sure is. That's it. So it's at the very pinnacle tip of the Juan de Fuca fracture zone. Remember what I said about stick points? There's only a few of them. Most of them are well-rounded over a large area. We got a stick point at Kamchatka, big volcanic eruptions in Kamchatka, and big earthquakes. We got a stick point down here on the coast of Japan. Well, lo and behold, stick point, big earthquakes, big volcanoes. Stick points down here, here, here. Well, that's where we get our other big earthquakes. So our stick points on the edge of the plate are spots where the wave gets caught up or reflected back. Either or, I don't know yet. Either or, we get an earthquake that breaks out on the tip of the stick point. In this case, last night, a 6.2 struck northwest of Vancouver Island, and that prompted me to issue the warning for California. Now, where did I warn in California? I warned right up here at the Bay Area. So we warned right here. Now, there's the earthquake that hit. It's within 250 miles. I'll definitely take that as an earthquake forecast. It's the largest in decades to hit Southern California. I'll take it. But there it is. So what happened here is there was a transfer of energy that went down the Juan de Fuca fracture zone. You see it here. It's like a lightning bolt shape. We can also look at it over on Google Earth. Even gives us a good view of it. Now, I've got my volcano place marks turned on here, so maybe I should turn those off. Hold on. There we go. So there's our lightning bolt-shaped fracture zone, Juan de Fuca, and then here's the Cascadia subduction zone, Washington, Oregon, Northern California. I can even turn the borders and labels on. There we go. So this zone here caught up a bunch of energy, but from where? How did it get inundated with energy? The whole Pacific plate went into motion. I just showed it to you. It spread up across through Alaska, put a amount of force on the edge of the North American Craton. Now we get back to that Craton talk again. So Craton, just a geologist word to describe the interior portion of the plate. Let me show you a diagram here. Put this diagram out 6 years ago with the black arrows on it showing you which way force flows. Comes down from the northwest, goes into California, also makes a bend over into the Midwest United States. Now look at the center portion of this, that rusty brownish color. That center portion of the Craton is the more stable portion, if you will. Now around the outside edge is the purple. The purple is the deformed edge. It's the mountain ranges. So the Craton edge is buckling, and as it buckles on the deformed edge, we get a series of earthquakes that break out. Now, professionals said none of this was possible. We're not going to be addressing what they said was impossible. We're just going to address that they said that the mountains were formed by glaciers and other things. Well, again, this is actually forming from buckling, seismic pressure that builds on the plate, just like over in Iran. Before we get into the United States, one more time, just like over in Iran or in Pakistan, Afghanistan, where we're bending across and around the edge of the plate, the interior portion of the plate and the exterior being the deformed portion, same thing goes on all the way over here in the United States. And our deformed portion making up a huge range going from, well, all the way up at the Montana border, all the way down through New Mexico. That's the Continental Divide, Colorado, the big 14,000-foot high mountains and so forth, all across the edge of the North American Craton perfectly. Now make note of the northwest edge of the Craton. The Craton goes right through Yellowstone National Park. As a matter of fact, Yellowstone lies right on the middle of the edge of the deformed edge versus strong edge, strong portion. So that's not a coincidence, is it? Now down to the south, all the way down through New Mexico and Texas, you'll notice the edge of the Craton makes a bend through Texas. So let's go in and take a look. This plays into forecasting. You've got to pay attention to all of this. So down through Texas, you see this U-shaped bend here. This is not a river. This is a 1,000-foot bulge or a rise. I can turn it in an angle. You might even be able to see it. So this is actually bulging up out of the plate. And this bulge is the southern edge of the North American Craton. And it makes a U-shaped bend and goes back up through here. Goes back up into New Mexico, and then you can follow the mountain ranges all the way back up. It's definitive all the way up to the north. And this edge of the Craton gets displaced just like what I was talking about in the West Pacific with the same sized earthquake spreading across the Pacific and then going into Asia, and we get the same sized earthquake spreading across the plate boundaries. Or like over in Europe, following the edges of the plate and their Craton, we get the same thing happening here. So the fulcrum principle applies as well as the Craton transfer principle. This is energy transferring across a region. As it transfers from region to region, a silent point is sought out, and then that silent point is hit by the combined total of whatever's on both sides, or all sides. Sometimes there's more than two that are moving. Sometimes you get junctions and plate boundaries that all get inundated, and you have to add up all the earthquakes. This gets into magnitude addition. So magnitude addition is when we add together earthquakes. 10 4.0s equals a 5. 10 5.0s equals a 6. 10 6.0s equals a 7. 10 7.0s equals an 8, and so forth, up the chain and down the chain. So if we start seeing multiple earthquakes, 20 2.0 earthquakes, that can add up. There's a cumulative total that adds up. Does that make sense? Now, this happens across regions. It doesn't just happen with this earthquake swarm in Southern California, where all this adds up. It actually adds up across whole portions of a plate. That takes us back to our fulcrum point principle. So look where our sets of rings overlap. We have one set of rings overlapping here on the Bay Area, just north of the Bay Area, defined by a 4 in the middle. This 4 in the middle between these two sixes, look at the positioning on this. It is the middle of the Juan de Fuca fracture zone, and I mean the direct pinnacle middle of it. The furthest most pinnacle tip, right next to the cleft segment south of the axial seamount that erupted back in 2015. So, middle fulcrum points are hit. There's a bunch of them here, aren't there? Everyone's going to get hit. Now, they're not going to all get hit with large earthquakes. We look to the nearest point now to our shallow large earthquake. Our first point to watch, obviously, where the two sets of rings overlap, the fulcrum point between the two areas that are moving, comes in right here on the Mendocino Ridge Gorda Escarpment, going down to geysers, north of San Francisco. How big do I think it's going to be? I think we have to take this 6.2 plus the 6.5 and possibly warn for up to a 6.6. I know it's a big earthquake to watch for in the Bay Area or north of it at Eureka, but unless something else happens, we could see energy transfer out over to the east and go over to Texas, Oklahoma, and Kansas, following the edge of the Craton like we would want it to. But this still means that we're looking at 4 and 5.0 activity going over into Texas, Oklahoma, and Kansas. And we'd have to warn everybody in the Midwest right now for 5.0 activity, which is what I'm doing right now. But same time, I'm explaining to you that this energy goes over to the Midwest, following the edge of the Craton. So right now, fundamental principle of forecasting is applied to current earthquakes here on the screen. Now, going forward in the future, anybody who watches this in the future, you'll be able to come back and see whether or not we got our earthquake developing out here. And then you might ask yourself, well, Dutch, what about down to the south? Same principle applies. We had a 3.5 to 4.1 earthquake to the south, and then this puts us in the LA Basin. The LA Basin, though, is one step beyond where we just saw our release. So if there's going to be an earthquake down in South California, very far south, LA Basin, I would put it right where the sets of rings overlap. This is east of LA, just southeast of the valley. So San Joaquin Valley, southeast of there, basically back at Glen Haven. That's basically where we're going. So I will warn LA, but it's going to be smaller than this 6.5, most likely. So the energy is going to build up between these sets of quakes, and then down to the south, whatever's not expended off this 6 is going to be striking down in LA. Let's put it at a 5.9. That's still pretty big. I mean, anything above a 5 in LA is enough to get news anchors diving under their desks. Time frame on this, 7 days. This is how we do forecasting as well. We have to get it down to 7 days. Why? For human sake. 7 to 10 days is what I've set my goals at, just like the weather forecasting. Now, we take it one step further than weather forecasting. Weather forecasting assigns a percentage on whether or not per day there's going to be rain or not. For instance, today, here at my house, they had a 20% chance of rain listed. 20%. Well, you just saw the big storm that hit my house. Now, I think forecasters do this to try to help and give odds of the chances of it hitting. Now, with forecasting, earthquake forecasting, we either do 100% or no percent. There is no 80% chance of an earthquake today. I don't agree with that form of earthquake prediction, and that is prediction. If you're going to say, 80% chance of this, that's not like weather forecasting in this aspect. We have to get it down to a 7-day time period. We have to get it down to a region. If I can get it down to a state, I'm very happy. If I can get it down to a 3-state region, I'm happy, extremely happy. And if I can get it down to a country, but hey, that's better than what they said could be done, which they said it couldn't be done at all. So if you can get it down to a country, if you can get it down to a state, if you can get it down to a region, you're doing good in the face of impossible, right? Somebody says something's impossible, you start doing it. So what applies here on the West Coast applies over to the east on the edge of the craton. There's an equal spread of force going over across Texas, Oklahoma, Kansas, Arkansas, all the way up the East Coast. One final point I'd like you to take away on this. Weak points in the plate are sought out by Mother Nature. This further aids in forecasting. If you understand that the drill points, whether they're oil, gas, geothermal, or Mother Nature punch points, volcanoes, ancient or new, that those weak points in the plate are sought out like perforations in a piece of stone. It doesn't matter how many layers those pieces of stone are, that if you perforate down through them, or even on the top of a few of them, force can seek out those weak points in the mass. And the same principle applies over plates, which is just phenomenal because this was all thought to be too big to happen across plates. I would like to point out, here's another equal distance spaced earthquake that just struck within the past few minutes, and look at the size of it, 4.5. So this 4.5 struck on the coast of Alaska. Well, it's the same size coming out of Japan from last night into this morning. Equal distance spaced, up, around, and over. That means there's still more energy transferring in. So let's recap one more time. If you're trying to learn how to forecast earthquakes, the first thing you need to look for are our deep earthquakes. Our deep earthquakes are the main player on the planet wherever they occur, and we watch for them to happen here at Fiji, where our letter D is. D stands for deep earthquakes, creatively. 2 here at Indonesia and South Philippines. 1 off the coast of Japan. 1 next to the Sea of Okhotsk and Kamchatka, Russia. 1D here over at the North Afghanistan border. And all the way on the opposite side of the planet, 1D down here at the Bolivia, Argentina, Chile border region. And these are the spots, you can see it, where we have our earthquakes raised high off the globe. There's earthquake forecasting right before your eyes. Letter D on the map telling you to watch for a deep earthquake. Deep earthquake strikes where the letter D is on the map. That means not only earthquakes are in a regular schedule and time or location, but it also means that there's a rhyme and rhythm to this. There's a tidal flow and ebb. Now that you understand the basics on this, earthquakes flow like a river. So this force that drops off the earthquakes flows out across the underside of the plates. I'm imagining in your mind's eye, coming up on the underside of the plate out of the magma, and then it hits the underside of the plate, starts to roll out on the underside of the plate, this force. And then it finds the cracks in the underside of the plate. Eureka, I can find a way up. I don't have to burrow through the plate. And then this force transfers up through the plate and starts dropping off earthquakes all the way along the way, as Mother Nature is trying to seek what's called equilibrium. It's trying to balance out this new introduction of power into the plates, and so it just follows the plate boundaries all the way out and away. And you're going to notice 5s, 4s, 3s, 2s, and then we get a reaccumulation back to 5s. So it's like a flowing river that spreads out in a delta and then reaccumulates back into a narrow channel. So what strikes down in South Europe strikes the Mid-Atlantic Ridge. What strikes on the west coast of the United States is absorbed by the plate and transferred across the plate, and big-time earthquake activity kicks up following the edge of the North American craton. Central America, South America, I mentioned I haven't addressed this yet. Force flows across, and it hits South America like a wall. It can't go through the plate. It's too solid. It goes around the outside edge. And let's get back over and look at our plate boundary map from the USGS one more time. So here in South America, you're going to see a few things. See the red lines? One goes up to the north, the other goes down to the south. Well, our earthquakes strike here, here, and here. The middle most inward point. So if there's pressure being applied from somewhere out here, it's then being exerted at the weak points, traveling across to here, traveling down to here, and then the middle point, that fulcrum point between here and here, comes under stress. Now looking at earthquakes, lo and behold, we have the same thing going on. It's a perfect match. Then going around North America to the north and going around South America to the north and going around South America to the south, we get the same sized earthquakes that strike here, travels down, around, and underneath the plate. Again, I told you, it's not going through the plate, it's too solid. So it's following, look, it goes down and goes over. It doesn't go all the way down and around usually. It travels underneath. And when it goes underneath, well, I mean, how could it? Look at the shape here. I mean, apparently there's a shallow portion of the plate here, and it travels down, around, and underneath. When it happens, when that force travels down, around, and underneath and ends up down here at the South Sandwich Islands, new eruptions begin to happen at Nevados del Chilean and other volcanoes down here in South Chile. So that's why we have our arrows there. We see the eruptions happen, then we see new earthquake activity. Same size, 5.3 here, 5.3 here. So first the 5.3 struck there, or a 5.5 now. They brought it up to a 5.5. First a 5.5 struck here, then a 5.3 struck down here within a few days. Same with up to the north, looking at the USGS plate boundary map. Look what happens. Goes across Colombia, over into Venezuela, and dead ends into the Eastern Caribbean. Then we have the Mid-Atlantic Ridge, no more than a hop, skip, and a jump away. Well, look at my map here. Let's turn off all the earthquakes. Look at our arrows. The arrows point on the interior portion of the South American craton, and it goes up across Venezuela, pointing right to the tip of the Eastern Caribbean. And guess what? Our earthquakes match this perfectly. Now, you might say, well, what about Haiti, Dominican Republic? Let's go over and look at the USGS plate boundary map one more time. Look, goes right through there. So the earthquakes can be traced back to here. Now, Guatemala. Look where the plate boundary comes through. Right through Guatemala, meeting up into South Mexico. What's right here? Fuego volcano erupting over and over again. It's on the Volcanic Ash Advisory Center now. And I haven't even checked that today, but Popocatépetl in Mexico. Ah, look, Nevados del Chilean in Chile is erupting right now. Hey, it hasn't been on the list all week. Same with Nevados del Ruiz in Colombia. Perfect example. So, Nevados del Ruiz is right here erupting. And down here, all the way at the travels underneath point, Nevados del Chilean is erupting. So we have a big push that's just come in, obviously. I mean, California's moving and big, deep earthquakes are happening. But that's where our eruptions are. Same with up to the north. Fuego volcano's on the list today, right here. And Popocatépetl volcano is on the list, right there. Coincidentally, both have earthquakes right next to them. Not coincidentally, that's actually something we expect. So I hope this has helped to clear things up a little. If you want to forecast earthquakes, the main key is finding those fulcrum points between the sets of earthquakes, taking the deep earthquakes into account. Of course, you can use the depth to magnitude conversion chart from Bella and Rebecca. That helps. But I will just tell you, as a general rule of thumb, you can look for a 1 magnitude larger earthquake off deep earthquakes that are over 300 or 400 kilometers deep. You start seeing a bunch of deep earthquakes, then you know to watch fulcrum points between our sets of quakes. And if you see a bunch of deep earthquakes across the whole planet, you know to expect major earthquake activity to take place across those regions. In this case, look at the regions from Fiji to Japan to Afghanistan, all the way back over here to South America, move down below in the plates. So, in other words, a big amount of force came up on the underside of the plate, not just in the West Pacific, but spreading to Afghanistan and South America. 3/4 of the planet had a displacement. That caused our 63,000 foot high blast stratospheric here, 55,000 at the volcano right next to it, caused a huge blast over here at Stromboli volcano just in this past couple days. It killed a hiker, very rare to get huge blasts at Stromboli. The earthquake activity spread across the plates following the plate boundaries and the craton edges. You can see it in Europe even. Up in Poland, and by the way, 2 people killed in Poland. That's 3 people killed this week in Europe from earthquake activity. How much more sign do we need that force transfers across plates when we see people in Europe dying from earthquake activity and it's following our big, deep earthquake event? Or we see the biggest earthquake in decades in South California. I mean, this has all happened in the same week. By the way, one final point I'd like to make on this. The warning signs that show up beforehand on the West Coast. Guys, there's things that happen beforehand that start to show up, like earthquake swarms, or the tar pits down at La Brea tar pits had overflowed, or the manholes that blew sky high in LA right after the tar pits overflowed, like the movie Volcano. If you start to see these things happen, they're Mother Nature's warning signs that there's a great amount of pressure in the ground. Energy has been introduced to the plate, and it's going to release, and it's going to find what we call our weak points. Now, our weak points, anybody can understand this. The weak points are usually Mother Nature made. I've described them internationally, fulcrum points and so forth. But once we get into a plate that's been drilled, for instance, or if there's a bunch of volcanoes that humans have drilled into to get geothermal, so I'm not just talking oil and gas. I mean, I'm not against steam, so I'm not against oil and gas either. I'm just telling you the drill points are vulnerable, the volcanoes are vulnerable. That further reduces your areas to watch. Now, we can even further reduce those areas by fulcrum point analysis of smaller earthquakes, but that gets into a whole nother thing. We're not worried about trying to forecast 0s and 1s and 2s. We're worried about trying to get it down for the 4s, 5s, 6s, and 7s. 4s in the U.S., 5s, 6s, and 7s internationally is what we try to get it down for. Someday, someone will apply these fulcrum principles, the standing wave theory, the SLF and VLF, the combined principles, and be able to do this in a real accurate method that I think gets it down to a few days' time. Right now, we're at a week, and we're at a region. If that's where we start, that's good. That's way better than where they started with the weather. Which, by the way, when they started with the weather, people said wind currents couldn't even be forecast. They didn't even have a word for it, forecasting. What was this forecasting? They were all calling it prediction. I call prediction when you get out your crystal ball. By the way, we're not using a crystal, well, this is a snow globe, but it represents the crystal ball, and we're not using a magic 8-ball. We're analyzing the areas that are moving down below the plates. We're watching that come up through the plates and spread out across the plates. As it spreads through the plates and across the plates, it finds the weak points, which are the plate boundaries. Then we get the drop-off of the same-sized earthquakes going across the entire zone. Look at this one more time. Imagine this going through a plate boundary and dropping off earthquakes along the way. And then new deep earthquakes hammering in on the underside of the plate like this, out of the magma. Huge, right? The combined force of Mother Nature's entire force on the underside of the Pacific plate, focusing in on a single point a few miles wide or less, and hammering in a new deep earthquake down in the magma. The force of the whole fluid hitting against a solid object. Think of a wave crashing against a flood wall, which is going to survive this conflict over time. Right? We all know the flood wall, the burial wall will get pulverized. Whatever rock is there is going to get pulverized. But then the force doesn't stop. It's not going to disappear. It's going to then be absorbed by the plate boundaries. And here's the wave tank example where a VLF wave is going, this is physical wave now, going through a wave tank. Well, the same principle would apply in the magma on the underside and through the plate boundary. That if VLF is going through the plate boundary and this tank represents the plate boundary, and we get a standing wave inside the plate boundary, and it starts to build in amplitude, what do you think is going to happen when it gets to a crescendo point? When it gets to a point where the feedback loop is too intense to be contained by the tank? Imagine if they kept hammering this thing in to where the waves were sloshing up out of the tank. Or think of a concert, a rock concert, where you're getting your feedback loop and you don't stop, you eventually will increase your amplitude to the point where it blows your stack, your speakers. So a feedback loop in a fault caused by VLF or SLF. Then, as the wave spreads out, it fills in its middle points. Look, each wave fills in each other's middle point with the same size wave. Now imagine that being earthquakes. Same sized earthquakes within a hair of a point of one another, filling in a fault zone, going across an area as this wave saturates the whole region. Speaking of wave saturation, I've got studies linked down below to pre-Coulomb stresses that have built inside plates, just detected, and they just put out the article this past week. I don't know too much about it, still have to read a lot on it, but pre-Coulomb stresses building in faults. Well, that to me sounds an awful lot like a pre-inundating force of VLF or SLF. Then the real question comes, where is the VLF and SLF coming from down inside the planet? Which I can wrap up this whole presentation by giving you guys a little bit of homework to do. Let me turn on my display capture again. And your homework is going to begin with searching this, Nepal Gorkha earthquake, VLF, very low frequency. And what should come up? I didn't spell Gorkha right, but okay, Gorkha. And you'll get a whole bunch of scholarly articles. Here's the nature.com. This is last June, so 1 year ago. The studies were released from 2015. And what they found was VLF, very low frequency, being emitted by Mother Nature up out of the plate boundary in Nepal before the big earthquake hit. Also found to happen in Japan. Japan 2011 VLF disturbance. Search that if you want additional homework to do. Japan VLF 2011 earthquake. There we go. Online library Wiley 2012. ELF VLF radio receiver operating was picking up some kind of emission coming up out of the plate. Now VLF is naturally only generated pretty much by one thing and one thing alone. That would be plasmas, like the aurora borealis up at the North Pole that happens up in the ionosphere. That aurora generates VLF. Air glow, plasma, that generates VLF. So Mother Nature is somehow generating VLF down inside the Earth, which is then coming up and hammering up in a concentric wave that you see on the screen here one more time. Concentric wave spreads out, starts a standing wave spreads out, drops off earthquakes along the way, and then the middle points are filled in by shallower, larger earthquakes as another jackhammering motion comes in on the underside of the plate. That's the principle explained, and then a solitary wave of translation takes place between regions where it spreads out, hits the end, comes back. Spreads out, hits the end, comes back. Each time it spreads out, it's dropping off earthquakes along the way, trying to find a path of least resistance from point A to point Z, and on the path in between, it's dropping off all these other earthquakes along the way. That is what I think is happening. I think I've explained my case pretty well, and now that you understand these fundamental principles of earthquake forecasting, you can start to do it yourself. You can start to watch for the fulcrum points. Watch for the earthquakes develop between the sets of other earthquakes, and you're on the right track. And then you can start to really get in depth on the deep earthquakes to shallower, larger earthquake conversion, see how that works for you. And I challenge every professional listening here now until you repeat the experiment. It's pretty basic, right? Finding the fulcrum points between the sets of earthquakes, watching for deep earthquakes, watching for shallower, larger earthquakes, and watching for progressions across the cratons. You have a roadmap. You have the craton diagrams already. Watch for the earthquakes to go around and follow it like a river. And then fluid dynamics comes into play. Fluid dynamics, wave dynamics, plasma physics. This would mean that there's plasma inside the Earth, guys. Now, I personally think, I know it's contentious, but I personally think that the core of the Earth is vaporized iron, uranium, the heaviest elements, that they're vaporized by a giant plasma torch, like a plasma ball. You know, those plasma globes you would play with that you can put your hand on the outside of the glass and the electricity comes up and touches your fingers, but it doesn't shock you because it's contained inside the insulator of the glass. I think the same thing's happening down inside the core of the Earth, and that electricity is, well, we know electricity is coming up from deep down inside the Earth and coming up through the plate, out through the plate, going up into the sky. Ground to cloud lightning. It's very seldomly the other way around. So it's ground to cloud, which means energy is coming out of the ground and going to the sky. Now, they say that's from a differential in power from the storm and the Earth. But that would mean the Earth has power. And if the Earth has power, where's it coming from? It's coming from deep down below, electrical power. And that electrical power is generating VLF, which is coming up out of the plate boundaries before large earthquakes. So therefore, since VLF is coming up out of the plate boundaries, it's coming from somewhere. And we know VLF has to be created by a plasma of some kind, naturally speaking. We don't think there's an earthquake machine down inside of the Earth. So it's Mother Nature creating this stuff. And if Mother Nature is creating plasma inside of the Earth, there's only one spot it could probably be done, and that would be down inside the core. That would be from vaporized iron, uranium, and other elements that are just basically acting like a plasma globe, but instead of your hands on the outside of a glass ball, you're talking about the plate on the outside as the glass ball. And then up above the plate, we're safe. But down below it, it's got to be highly charged electrically in plasma. That's my contention. That's it wrapped up in a nutshell. Look for your fulcrum points. California is a perfect example to watch in the next several days. And I will get back on and address it. I'll probably do another update. At some point, I'm going to get a video professionally made. A professional production. Maybe I need to hire a production company where they, 30-minute production, some kind of thing that could be put on TV. Right now, it's live stream quality. It is what it is. I am who I am. I am a high school grad. I have no degree in the fields whatsoever, and that's probably good because a lot of what I found and what I've apparently discovered contradicts and conflicts with everything that's in the textbook or taught by professionals, which is really upsetting them, by the way. Not really worried about that. That's the way world of science works. You make a discovery, it conflicts with everything. Eventually, they have to tear out whole sections of the textbook anyways and replace it, and that's where we are. I hope you guys got something out of my little broadcast here. I'm going to save this as a video over on YouTube, and we will get it out to the world as titled, How to Forecast an Earthquake, Fundamental Principles. Maybe that'll be good. Just the fundamental principles behind how this works, how the pressure transfers, how energy is absorbed and transferred between plates, and it does. And the fulcrum point principle is just, I started to notice several years ago that these middle points between our current earthquakes on the map were getting filled in. So like I would see these two earthquakes here in California, and then within a few days, a new one would fill in that middle point. I'd be like, wow, this looks like a piece of art. They're perfectly overlapping. It looks like Da Vinci's, thing of with the person divided in half. What's that called? A Vicia Pisces or something? I'm not an artist. I don't know. I'm not into geometry either. But it is a proportional geometrical distribution of force across a mass. That's the best explanation I can come up with. And I, again, have worked on this for years, and this is all based upon the observed. And now I've given you my ideas behind why I think it's happening. I've shown you the wave video, and I've shown you the standing waves, and I've shown you the equal distribution on both sides. Okay, those are my ideas behind why I think it's happening. There is no debate. This is happening. There are earthquakes spreading across the plate boundaries, and they are the same size, and they're going in a certain direction over a week, and they're starting in the West Pacific and ending at the Mid-Atlantic Ridge for Europe, and they're starting in the West Pacific, going around Japan, up through Alaska, and down to the United States, and then across the United States, following the Craton Edge. These are all things that we've observed. I am not going to accept that these aren't happening. That's documented in video. The only question now is why? Right? That's the only question now is why is this happening? Why are the fulcrum points getting hit? Why is there a progression of earthquakes across the Craton? Why is there an equal distribution of force across the West Pacific? I mean, I would say fundamental physics says so, that's why. But other people might have better answers. I don't know. This is a debate to be had by people for the next 150 years. I just happen to be the guy who stepped in the big, deep pile of it and brought it out to you guys. And it's been a hell, storm here and back, but it's been worth it. I believe in the observable science that I've professed for years. It's not just something that I preach, it's something that I live by. And people said that it wasn't happening. If you knew the story, you would laugh. People said that I was working for the military. There's a guy on YouTube who made a video who said that I work for the military and that I have an earthquake machine. We'll just leave it at that. I'll go tune. Do I have an earthquake machine? Do I have an earthquake machine? Hold on. My sources say no. All right. And we're going to sign off on that. You guys have a good morning, afternoon, night, evening, Truman Show style. Everybody's watching. I'm going to get this out as a video over on YouTube. Peace out.